So I'm Michael Staib. I'm a GraphQL TSC, and I'm also the founder of ChilliCream, which is a company that creates open source tooling in the GraphQL space. Today I want to talk about distributed GraphQL and more specifically about GraphQL Fusion. That's a new specification that the Guild and ChilliCream developed together, and that we are putting under the GraphQL Foundation so that we have an open specification in the distributed GraphQL space. But let's start at the beginning. So when we talked about GraphQL with customers or explain GraphQL to people, we are always talking about this unified API where you have all these clients that can do the perfect fetch against this API. And that really revolutionized how we interact with APIs, because instead of telling the user that you can do these requests against something, we suddenly have this human readable API model that you can reason about. And that is actually where also Facebook came from when they had GraphQL. They had this big monolith that they put on their ends API, I think, or on your business layer or whatever. And that really was a good approach. But the moment GraphQL was open source, what actually happened is that people started putting GraphQL over the existing infrastructure. And this happened because front-end engineers saw GraphQL and saw the impact that would have to their type of work. And that's why they didn't want to wait for the backend engineers and just took GraphQL and JS and wrapped the existing infrastructure, their existing REST APIs, basically into GraphQL, and suddenly had a much better experience. Also much better performance, because we didn't aggregate data anymore on the client side, but now close to the actual REST APIs or what you had in your backend. But it also gave a lot more richness to your API model, because you could reshape these REST APIs. So GraphQL, very shortly after it was open sourced, actually became a gateway technology. And that's something I want to lean into, because I think not only that GraphQL makes the perfect communication protocol between your clients and your backend is what GraphQL makes great. It's actually that you expose a model that hides the implementation complexities of your backend infrastructure, like that you have microservices or that you have REST service behind that. So when we talk about GraphQL or distributed GraphQL, we are actually just swapping out these arbitrary services against GraphQL services. So our downstream services become GraphQL services, and we typically call these subgraphs. So we have a GraphQL gateway, which actually is composed of subgraphs. And it doesn't really matter the technique of how you do that. It's basically what each of these approaches would do. Behind these subgraphs are often other infrastructure. It could be microservices. Doesn't have to be, right? But could be. Could be gRPC services that you communicate behind. And typically we do distributed GraphQL to scale. But we don't do it to scale like throughput or whatever. So if you have a team of 2 developers, don't even think about distributed GraphQL. Just stick with a modular monolith. It's a much better approach. But if you have the scale needs, you have lots of teams, lots of developers that are basically competing about updating this gateway, your composed GraphQL schema. Distributed GraphQL is really a good idea, because now we can have organizational responsibilities, like teams taking responsibilities about part of your graph. And for this kind of thing, we actually have a lot of solutions. Like there's Atlassian Nadel. I don't know if anybody knows this. Nadel actually means needle, is a German word for needle, and was created by Andy, the maintainer of GraphQL Java. So there are other techniques like schema stitching, and we have schema stitching in several flavors. There is GraphQL Mesh, which also is a great solution. It lets you aggregate not only GraphQL, but also OData and OpenAPI and whatnot. And then there is Apollo Federation, another approach that had another take on federated GraphQL APIs or distributed GraphQL APIs. What all have in common is that they are not using an open standard. So there's no open protocol that they use which allows us to exchange the tooling that we use. Like typically when we have such a complex setup, like distributed GraphQL setups, where we have all these subgraphs and all these teams competing to update the schema, then we also need a lot of tooling. Like a linter might be a good tool, but then there is like schema registries, client registries, there's telemetry, there's tons of tooling involved to make that really a good experience. And that's where we actually don't want a vendor lock-in. We want to have these things exchangeable, where I could take, for instance, the schema registry from the guild, just take Hive, and then I take, for instance, the ChilliCream gateway and just combine them, because that are the tools that make the most sense for me. So back last year, we met actually up as companies. We incidentally met at the API days in France, and then we started talking about actually this problem that we have with distributed GraphQL in our ecosystem. So what we decided there is to formalize all the knowledge that we gathered in the open source space with distributed GraphQL and write an open specification that everybody can take part in and everybody can build tools around to open the space up. So what we need is an open solution for distributed GraphQL. And that's actually where GraphQL Fusion comes in. So when we talked about what is actually making up, or what are actually the components of a distributed GraphQL setup, we came up with 4 major components. And this we came up, actually we did every Tuesday, we would do 1-hour sessions with all our company engineers and looked at this and looked at how we can standardize that. And this we did over a year. And then we started writing on that, a spec. So there are 4 major components that you will meet in any distributed GraphQL setup. One is the schema composition. And the schema composition is basically describing how you merge several subgraph schemas into a distributed gateway schema. Then there is something that abstract we could call the gateway configuration. The gateway configuration doesn't need to be a JSON file or whatever. It could also be just a GraphQL schema, an SDL schema, which is heavily annotated. It's basically what you feed into the gateway, and the gateway is then able to distribute queries across your subgraphs. The third component here is a remote executor. So the remote executor knows how to interpret this metadata and then issue all the requests to your subsystems. Last of that, and that's actually not part of the Fusion specification, is telemetry. So we did a lot of work around telemetry, but let me point that out later. So the Fusion's core spec is concerned with these 3 initial components I set here. Okay, one of the key things that we thought when we started on the spec was that we want to embrace GraphQL. That means that GraphQL features, or what the capabilities of a subgraph is, should not be due to a subgraph protocol. It should be up to the GraphQL spec level of a subgraph. And also we want to allow any schema to be a subgraph. It shouldn't be that you have to implement a protocol which actually creates a very bad GraphQL server to be what you have to do to create a subgraph. You should be able to integrate anything. Like if I wanted to have GitHub data, I should be able to just pull in the GitHub public subgraph. Not a good idea, by the way, but I should be able to do that, and it should be able to compose and let me create a valid distributed GraphQL schema. So another thing here is we wanted to support and use all GraphQL best practices and patterns that are out there. There are, for instance, the GraphQL global identification patterns that we use in Relay. This is actually something that we can use in a distributed GraphQL setup, and we also want to use the node pattern to resolve these nodes and not have difficulties implementing that just because we do distributed GraphQL, right? So let's talk about the schema composition, because that is one of the first algorithms that we looked at. So the Fusion specification not only is a bunch of directives, it also has strong algorithms on how to merge schemas and how to execute schemas, how to get a query compiled into a query plan. So when we look at schema composition, we're actually focused on the subgraphs and their type systems. So when you think about schema composition, it's important to think about what does it mean if I have similar types across my subgraphs. So if I have a user on the account subgraph and the review subgraph, what does it actually mean? Is that a collision, or are these semantically the same types that we want to merge? So what Fusion does is basically saying these types are semantically the same. If they are not, you can rename them. So when we take these types, we would basically merge them, and then, we would basically merge them, and then they would become one type. There are difficulties around that because, like, it could be that you have different nullability settings on your different subgraphs. Like maybe ID on one subgraph is non-nullable, on the other graph is nullable. And these rules, these algorithmic rules, are basically defined in the Fusion specification, how this is handled. Like, for instance, if one field is nullable, basically the overall type will have a nullable field because we cannot guarantee that it's not nullable. There's also like the way how we handle overlapping fields. That is also part of the Fusion spec. Like overlaps allow you to create more efficient query plans because now we can use these overlaps to determine how to most efficiently fetch GraphQL queries from your subgraphs by avoiding too many hops between your subgraphs. Okay, let me hop over that. And let's actually look at GraphQL Fusion. I did a couple of introductions here. So let's actually compose a GraphQL gateway and have a look at a couple of cases here. So let's start with a very simple case. I have here a GraphQL gateway with the 4 subgraphs: account, products, reviews, and shipping, basically a little shop. So the first thing is I want to compose this account subgraph into my gateway. And that is the first thing I talked about, schema composition, and we want to compose that into our subgraph configuration. So what we do is we use our Fusion CLI to compose at build time. The Fusion spec doesn't tell you to do that at build time. You could also create a gateway that has runtime composition if you want to do that. It basically is concerned with the algorithms, how to compose the gateway schema. So what we can do here is say Fusion compose, and then we take the subgraph and say, take this subgraph, compose it into a gateway. So if we do that, and we look at our gateway, we can see here we have a Fusion GraphQL. So the Fusion GraphQL, let me actually make that a bit bigger, has just a couple of directives. So don't worry, you never have to write them, they are composed. And we just have a couple of them, like an intermediary language for your query planner. It basically tells you, query planner, all the options that you have to resolve a type or a query. If you look, for instance, at the user type, you can see we have two kinds of variables here, variable and directives, variable and resolver. So variable is how to aggregate state from your type relative to your type. So in this case, I can get the user ID by selecting the field ID from my type here. And then I have here a couple of resolvers, and depending on the resolvers, these demand a certain state, like certain variables. So when the query planner now looks at resolving a query, it will pick the best resolver for the case to resolve your fields, but also look at the state that is available already from a previous GraphQL query plan step, and then formulate the most efficient query. We also have annotations here, which field is actually available on which subgraph. At the moment, it's very simple because it's all on the account subgraph. Okay, I could actually go here to my schema now that we just composed. Look at our schema here. Let me refresh that. And then we can see that we only have here the basic accounts field, right? Not very enticing. If I would query that, actually now, I would probably, let's quickly do that. Notes, and let's get the name. I will get here a simple response, and if I look at the query plan, I can see we are just fetching from one subgraph, then we are composing the result, and then we are done. So let's make it a bit more complex and actually feed in another subgraph. So in this instance, I want to add also the review subgraph. Basically, I have the users and the reviews these users write. So for that, let's just put this subgraph in here. Now, commit that. And then I get a much more annotated schema here. You can see there is a lot more annotations going on, but it's basically the same kind of annotations. Let's actually look at our user type again. Oh, that was wrong. And if I look at that, I can see there are a lot more entity resolvers to my user. So I have now here a couple of these resolvers that allow me to fetch the user by ID from the account subgraph, but also from the review subgraph. Because in this instance, the review subgraph also is able to resolve any user. If that is a good idea between two subgraphs, depends on how you design your subgraphs. It could be that you are only able to resolve the user from one subgraph and then just complete some data from another subgraph. This is all dependent on how you compose these subgraphs. One important aspect is that we don't use any hidden fields here. We are actually using the resolvers that you use to build your subgraph here. When I look at the schemas of the subgraphs, that is how you would build a GraphQL server. And that makes for a much better telemetry. If you look at like OpenTelemetry ingests, then you can much better reason about what's going on in these GraphQL servers and what do I have to do to optimize data fetching. Okay. So let's try that a bit out. We have here a couple of resolvers. You can also see that we reuse the nodes resolvers here because we reason about if that is a node actually, it has a unique key, so we can use that to compose your gateway. And then we can batch with the nodes field here to fetch data. So let's do that a bit. So I can actually go in here, fetch the users, and actually let me refresh the schema here, and then go into the reviews now that are now available to me. And we go in the nodes here, and then we get the body. So this, if you think about it, should be coming from two subgraphs now. But actually, it's just coming from one subgraph because we have overlapping data, as I explained in the beginning. So the query planner looks at this and says, okay, I actually can get everything of that from the review subgraph, because the review subgraph actually has the username, because that makes sense that we have the name of the author for every reviews. But if I opt into things that only live on the account subgraph, suddenly I get a query plan that is made up of 2 query plan steps here. And if I would look into detail here, so the query plan can also be exposed as an extension in my result here, and I can actually have a look at what's going on here. So the query plan has here a sequence step. That means these query plan nodes have to be executed one after the other. Then we are going to the reviews graph, resolving actually the query that we want to do for the reviews, but we are also exporting here an ID, and this ID is actually the user ID. We collect all of these, and then in this case, because I don't have a clean batching field, we are reusing the nodes field to then get the user details that just live on that result, on that subgraph from the on the account subgraph. So that's a very basic example how easy it is to compose these things. There could be a lot of custom extensions around this, like the Fusion spec defines the basic algorithms, but that doesn't hinder anyone to implement a bit more on top of that, to go beyond beyond the initial use cases and enrich the composition process. The important thing is that we always compose this standardized GraphQL configuration for our gateway that we can then use to distribute queries. So let me show you one more thing. Let's compose, for instance, a more complex thing here, because we also have 2 more subgraphs, and I'm quickly going over that. So let's take, for instance, the product subgraph, and then I have actually here a shipping subgraph. And sometimes you have a schema where you have maybe here the delivery estimate, which is an algorithm, where I actually want to estimate the delivery for a product. So I have to pass in here zip. That should be passed in by the user. But I also have here a couple of other things like weight and size. These are requirements that I actually have to other data from that live on other parts of my subgraphs. So ideally, I want an API that only exposes a zip here, and this is filled in by the execution engine. So this is where we could require data from other subgraphs. To do that, we don't want to actually change our GraphQL subgraph schema, but we want to kind of give our composition some hints on how to compose. So what we can do is actually add another GraphQL file here. You could also have annotations or whatever you want to implement here. But we could also just put here a GraphQL extensions file. GraphQL. Sorry for that. And then we could implement here or add some annotations to our schema. Actually, that in. We extend our product here. I basically repeat here my delivery estimate field from the product, and then I can annotate it. And I could say, okay, this field is actually requiring the weight. So I'm describing here relatively to my type how to require data here, in this case from dimension and weight. I want to have this data relatively to my type here. And the engine should fill that in and actually figure out where to get that from my subgraphs. It is guaranteed that if I do something wrong here, that the composition would say, okay, this data lives nowhere. There's no subgraphs that could fulfill that. And then we would opt out here and get a compilation error. Same goes here. I actually don't want to require the zip. That was GitHub Copilot. Sorry. I want to require the size here. And then this should be automatically fed in. Let's actually compose that. Fusion compose, and we put the shipping graph in. And then let's go back here, refresh our schema a bit. 5 minutes, okay. Okay, and then we could, let me go here. No, there. Okay, I didn't have that, so let's type it out. So in my case, I could go here to the reviews, and then I could go to the product, and here's the delivery estimate on there. And if we dive into that, you can see just the zip code is now here. I can fill the zip code in with whatever, because it's just demo. So, and then I could ask for the maximum time it takes for this item to be delivered. If I execute that and go into my query plan here, you can see there's a much more complex query plan. Because we are not involving 3 subgraphs, as you could imagine, we are actually involving all 4 subgraphs. Because first we go to the reviews, get all the reviews. Then we are going here and batching all the IDs that we gathered here. In this case, the product ID and the user's ID that we get from the first request. We batch that in parallel to the account subgraph and to the product subgraphs. These can be resolved in parallel. Then we do some composing of the data. And at last, we are fetching the delivery estimates. So that's an easy way to get like even more complex cases done. There's a lot more that you can do. I don't want to go too much in all the details that we can compose here, but the main message here is you can compose like standard subgraphs, and you saw I didn't have to do a lot to my subgraphs to change them, and I was able to compose a complex graph from that. And it even performs very well because I get this rich query plans out here that find the best way to fetch the data from your subgraphs. Okay, and just rest assured, this also works with subscriptions. So if I go, for instance, just here, we can also just as easily subscribe to this data. As soon as I have a subscription in there, I can also execute that. Actually, let's skip over that and go back to the slides because I have 2 minutes. Let's talk about query planning. So the Fusion spec describes a basic query planning algorithm, so everybody can implement that. Like implementations, like our implementations, go actually further. We have a PGO approach, the profile guided optimization approach. That means we will quickly generate a query plan that is kind of okay. And then we take in telemetry, and we're using OpenTelemetry. We are working with the OpenTelemetry community to get a better semantic convention. That's the work that we are doing actually with Staib, also a gateway company. And we have a draft of that, and we are using that to do these profile-guided optimizations. That means after the initial query plan is issued, we will fetch the telemetry that is coming in, and then look actually how the subgraphs behave, if there are better subgraphs, faster subgraphs, and then we issue like new query plans to try out if we can find a better way to do. That's complex, but this is where gateway companies actually can make the difference and implement unique solutions to these things. But the good thing is that the spec gives you, like the GraphQL spec, a very good outline to implement all this setup. There's one more thing. Behind this spec is now not only just the Guild and us, there are a couple of other bigger players, like AWS is helping us to push that a lot. And there's IBM, Hasura, and many more. If you have questions, just approach me, because I think I used all the time up. But you can meet me outside and we can talk about that. If you want to connect to us, you can grab anybody of the Guild, or you can go to anybody with this logo, like Pascal, for instance, and talk to us about GraphQL Fusion. Thank you.